Yo, what is good? Got some questions here. Today we're going to move on to coordination chemistry. We're done with solubility, things like that. Did all the questions that I have for that, so we're just moving on to coordination chemistry. I luckily got to catch up on this because I got a midterm coming up on Monday, and I honestly am quite rough on this topic. um, as you can see by these questions, these are very easy, basic level questions because I haven't really fully understood what I'm learning yet. So we'll just leave that for a bit later. So the first thing we're doing is just writing out the most probable electron configurations for the following kind of species, if you will. But yeah, I guess we could just get started. So electron configurations, I don't really know how to explain. It's just they just show how many electrons that, they have. Like we have. Actually, wait, I have a periodic table here. So hello. What is this? So we have the S block. Yo, can I not draw on this? Wait, why is it frozen? Yo, what the heck? Oh, okay, there you go. My bad. Yo, is this good, bro? Okay, so we have here the S block. Then we have the D block. Here we have the wait. I look, you forgot what this is called. Wow, I have a cough that's not going away. S. Oh, okay. This is going to be the P block. And helium is considered the S block, so I'll just put that there. And then these here, this is the F block. So yeah, honestly, that's a pretty basic introduction to it. I don't really know what else to talk about for this one. It's still honestly pretty simple, but so we have these ions that we need to find the electron configuration for. First we have cobalt 3+. So the way I like to do it, or the way that makes more sense when I'm starting to, or when I was learning to do it, is just draw the basic cobalt, cobalt neutral, and cobalt is right here. So we're gonna just be doing the simplified just based off the having the previous noble gas. Otherwise we have to write 1s2, 2s2, 2p 1 2 3 4 5 6, 2p6, 3d2. We're just gonna have to keep on writing that redundant stuff, but we could just keep the previous noble gas in brackets, and that'll show what it is. Yo, this is actually getting a bit annoying, bro. Why is it glitched? AR. So what that bracket represents is just following everything up to here. It's representative of all of this by drawing it like that. So that's why we draw the square brackets around the AR. Wait, one sec, I got a cough. Yo, I don't know what's going on, bro. Okay, so now if we know and represent it up to AR, we have to just show K, CA, and all of these ones here. You have to represent those, show it and write it out. So yo, my throat is actually killing me, bro. Okay, so we got 1 2 3 4. So in the S block we already have it full because we need to get up to cobalt, and we're going to fill 1 2 right there. So that's going to be 4s2. Boom, that's done. So now we have to fill in the D block. 1 2 3 4 5 6 7. This is going to be D7. 4d2 D7. Simple, right? But that's not what we're looking for. We're looking for cobalt 3+. So we have to remove 3 electrons. Now, you might be saying yo, what if we just count backwards from here? That's what I used to think. What if you just go 1, 2, 3? Then we should be at 3d6. I mean, no, not 3d6. We should be at 1, 2, 3. We should be at 3d4. But this is not the case because keep in mind, 4s2, 3d7. I don't know, I forgot to write that. But 4s2, that means the 4s is at a higher energy level. And if it's like, if we got like a energy diagram and we got like an electron here, an electron here, this electron is going to get taken out first, and then this one will go. We don't want to take out the electron that is lower, because that's just more work to do, because it's like closer to the nucleus. It's going to have more like, binding power, if you will. It'll just be more attracted to the nucleus through the positive negative charge. So you want to remove the farthest away electron, and that's going to be the 4s2 electrons, because those are the highest level. So we need to remove 3 electrons. So we're going to remove, because there's 2 electrons in the 4s2, so we're going to remove 2 electrons from the 4s2, and then we're going to remove 1 electron from the 3d7. So we're going to be left with Ar3d6. That is the electron configuration for cobalt 3+. Pretty simple, yeah? I would say so. Bro, this cough is actually so annoying, bro. Okay, so that's the next one, Fe3+. So we'll start it with doing iron, just the basic one. So what we should get, let me just erase these drawings real quick. Well, it's not letting me erase. That's a bit of an issue. We'll just erase this. Oh man. Okay, so iron is right here. So we're still gonna have the same noble gas, which is gonna be argon, I don't know. But so we have 1, 2, 3, 4. There's gonna be 4. 1, 2, 1, 2, 3, 4, 5, 6. So now we need to remove 3 electrons. So this goes, and this goes. So what we'll be left with is argon 3d 1, 2, 3, 4, 5. Argon 3d5. Boom. There you go. Pretty simple, yeah? Okay, now let's do MO. What is MO? I don't know. Okay, where is MO on the periodic table? Oh, man. Bro, I can't even, like, cough normally, bro. Like, it's just, like, stuck. Pause. But it's just there, bro. Okay, MO is right here. Okay, so we're going to start with Kr as our, is that krypton, I believe? Yeah, krypton, xenon, I don't know, argon, neon, helium. Okay, so Kr, that's going to be our noble gas. And then we have 4s here. 1, 2, 1, 2, 3, 4. So noble MO will just be 4s2. Wait, no, this is 1, 2, 3, 4, 5. So this is going to be 5s2, 4d. Kr 5d2, 5d2, 3, 4d4. Can I turn this off?
Yeah, I forgot.
My fault. My dad just came. Anyways, so we got 1, 2, 3, 4, 4s2, and then we got 1, 2, 1, 2. So we need to get rid of 4 electrons. So we're gonna remove them from the 4s2 level first, and then we're gonna remove 2 of them from here. So it's gonna be 1, 2, 3, 4. So we're gonna be left with just the inner gas configuration for argon. So it'll just be Ar. So it's like happy. PD. Where's PD? Bro, this is so redundant, bro. I look, you don't know if we're gonna do the last second question, bro. I'm trying to go to sleep. And this thing just keep on glitching, bro. Where's PD? PD is right here. Okay, so it's gonna be 1, 2, 3, 4, 5. 5s2, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. And it's just PD, so there's gonna be, bro, why is it so glitching, bro? 5s2 but wait, something is wrong. Now, something you want to notice here is this is an exception. Why is it an exception, you might ask? Well, so if we have, bro, why is this glitching, bro? Oh my god. Okay, so you know in D we have 5 orbitals, right? So, and it's more like electrons like to stay like half filled, like this, or they want to be full, like this. So in this case, right, PD is 1, 2, 3, 4, 5, 6, 7, 8. So it's gonna be at 8, right? So if we 1, 2, oh my god, 1, 2, 3. Okay, cancel this out. Cancel this out. So here, this electron configuration, it's really close to being full, right? So what's gonna happen is that these 2 electrons here are just gonna go into the D subshell, and we're gonna get fill these 2 in. 5s2 will disappear, and we'll have 4d10. Boom, there you go. Pretty simple. Explanation. I'm actually getting railed by school, bro. Like, yeah. Anyways, this is the electron configuration for PD. What's the coordination number and oxidation state of the metal within the complex ion? This should be easy, bro. Why is this cough? Yo, this actually making me mad, bro. Okay, coordination number. Coordination number is basically just the amount of like connections it has. So, something you should know: ethylene diamine. It takes a coordination number of 2 because it connects 2 different spots. So, with this example here, this question, we're gonna get 2 from here, and then we're gonna get 4. So Cn equals 6. Simple. Now, what is the coordination number? What's the charge or the oxidation state? Well, we could just do that by looking at the charge. So we have an overall charge of -1. Cl4, that's -4. En is neutral. Is it? Yes, it is. 0. So now, what charge does cobalt need in order for the overall charge to be -1? Well, let me let you think for that. Well, I don't even know what I said. It's going to be +3. +3 minus 4 equals -1. So oxidation state is equal to +3. AuCl4 H2O 2. So we have overall. We need to find the Cn number, right? Okay. Oh my god. Okay, so we got Cl. This is going to each be one coordination number. This is going to be each 2. So Cn equals 6, similar to above. Now the overall charge is -1. H2O charge of 0. Wait, tomorrow's I have OChem again? Oh my god, bro. I thought OChem was today, bro. Oh my god. Okay, Cl4, that's -4. Overall charge is -1. What charge does silver have to be? What does it have to be? I don't know. It's going to be +3. Why is it going to be +3? Well, 3 minus 4 equals -1. Simple math. Hope you figured that out. Cn6. So C coordination number. Oh wait, that's like the same thing. It's gonna be 6. Why is it gonna be 6? Because each cyanide will give a coordination of 1. So then you multiply that by 6. Now what's the charge? Well, the overall charge is -4. The cyanide ion gives a charge of -6 overall. So now what do we have to get to go to -4? Well, hope you guessed it. It's going to be +2 because +2 minus 6 equals -4. There you go. Hope you enjoyed. See you tomorrow. Goodbye.